Hi everyone, in this lesson we'll look into various forms of solving quadratic equations. But first, let's take a look at some conceptual terms that will help us understand what it means to solve a quadratic equation. Now remember that the equation of a quadratic function in standard form is y equals ax squared plus bx plus c. So basically this is an equation. Independent variable is x, dependent variable is y. So when you think of the solutions of this quadratic function, the solutions will come in ordered pairs, x and y. And when you look at the graph of a quadratic function, we're going to say that all the points with coordinates x and y that satisfy the equation will lie on the graph of the quadratic function. And when you think about it, there are how many points on the graph of a quadratic function? So it is very hard to count them all because there will be infinite number of points that lie on this graph, which means that there will be infinite number of ordered pairs that satisfy this equation. And the ordered pairs that satisfy the equation are the solutions to this quadratic function. So we're going to say that the number of solutions to a quadratic function is infinite. And the reason why is because the coordinates of any point on the graph of the quadratic function can satisfy the equation, and there is an infinite number of such points on the graph. Now, very often when we solve problems that can be modeled by quadratic functions, we're interested in knowing specific points on the quadratic function, on the graph of a quadratic function, such as the vertex. Remember that last class we looked at how we use the vertex to solve problems where we want to identify minimum or maximum value of a quantity. And sometimes we want to know what the zeros of the quadratic function are. And the zeros of a quadratic function means where the y value of the quadratic function is going to be 0, or when ax squared plus bx plus c is going to be equal to 0. So ax squared plus bx plus c is 0, where y equals 0, and y is equal to 0 at the x-intercepts of the graph of a quadratic function. So we're going to say that the zeros of a quadratic function are the x-intercepts, and they're also known as the roots of a quadratic function, and I'm going to talk a little bit more about it later. Or the solutions because we're looking into these points. So those are the solutions to our problem. Now, the reason why we call them the roots is because there are many quadratic functions that can have the same x-intercepts. So when you think about it, this quadratic function has the x-intercepts at -4, 0, but how many parabolas or graphs of quadratic function can you draw with the same zeros? So you're probably thinking that you can draw a graph that looks like this with same zeros. Sorry, this is not a perfect parabola. Or you can have a graph that looks like this, for example, or you can have a graph that looks like this as well. Now I want you to think, what is the difference between all these graphs that have the same zero? So what makes them have different kind of shape? I mean, the shape is parabolic, but different kind of orientation, that would be the better word. But their roots are the same. So you probably have thought that the reason why would be lies into the value of the coefficient a. So when the coefficient a changes, the parabola can become taller, or it can become wider, or it can open down, or it can open up. So functions that have the same x-intercepts, they're fixed on the same axis, on the x-axis at the same points, but different coefficient a, say that have the same roots because they're built on the same fixed points, and they are called functions that belong to the same family, or they make a family of quadratic functions, and that's why we call them roots. Families, most of the time they have the same roots, right? So algebraically speaking, we can say that we can find the zeros of the quadratic function then by making y equal to 0. and then we solve for x. Now, I want you to take a look at this very, very, very important definition that we're going to look into now. So, what you see in here in red is the equation of a quadratic function, and what you see here in purple is the equation of the zeros of the quadratic function. So when you look at this, you see that the right sides of these two equations are exactly the same, but the left sides are different. So this one here has a value of y, and this has a value of 0. So which means that a quadratic equation, which is short for the zeros of a quadratic equation, will tell us at what x values the y is 0, so the value of y is known and it's equal to 0, whereas in this equation, the value of y can be any number, and this is called a quadratic function for short, quadratic function, and this is called a quadratic equation for short. So try to distinguish the difference between the two. And one way to actually remember this is to understand that this has infinite number of solutions and this has a limited number of solutions. And we're going to talk about the possible number of solutions next. Now, if you look at these two graphs, you see that this parabola opens up, this parabola opens down, which means here A is positive and here A is negative. We're not going to look into what exactly the value of A is or what exactly the the coefficients are, like the equation is, but we're going to focus on the number of zeros. So as you can see here, the graphs intersect the x-axis at 2 points. So we're going to say that the equations of functions represented by these graphs will have two real, distinct, meaning different zeros or x-intercepts. Now, in the next example, you see that one of the graphs here, let me make them a little bit more pronounced, we'll have an x-intercept right here at x equals -1. And this graph here has the x-intercept at x equals 2, +2. So in this case, you see that the graph has only one x-intercept or one 0. And normally, what we call this in the past is an equation with one solution or one root or one 0. Now, we're going to change the naming a little bit differently to add more space to the definition. So, first, I want you to think, can you figure out the equation of this parabola? And that's something that we have learned how to do in earlier grades. So, in order to determine the equation of a quadratic function, you can start from y equals ax minus h squared plus k, especially when you are given the graph of it where you can identify the vertex. And that's why we want to use the vertex form of the quadratic equation to find the equation. So, the value of a is always going to be the step pattern that you find starting off the vertex, moving over 1, and then vertically up or down, so whatever the case may be, to hit the parabola again. And in this case, it seems that we're moving 1 unit up. So that will make the value of a, in this case, equal to 1. Now, the value of h will be the vertex, x-coordinate at the vertex. So in this case is -1. And the value of k would be the y-coordinate at the vertex, which in this case is equal to 0. So we're going to say that the value of k is equal to 0. So the equation of this parabola will be 1 x minus -1 to the power of 2 plus 0, or for short, y equals x plus 1 squared. So if you want to find the zeros of a quadratic equation, then you're going to say that y has to be 0 if x plus 1 squared is 0. Now, if you were to solve this equation by using the factoring method, then you would have to say that x plus 1 times x plus 1 is equal to 0. That's the same as saying x plus 1 squared is equal to 0, right? And to find the zeros, we make each factor equal to 0. So we say x plus 1 is 0, or this other x plus 1 equals 0. So remember that if this is 0, you multiply by anything, you're going to get 0. And if this is 0, you multiply by anything, that would be 0. So you're going to say that the roots are -1 and -1. So basically, we do find not just one but two roots, but they are equal in value. And in a case like this, we're going to say that the equation of a quadratic function will have two real equal roots, or two equal real roots, or solutions, or x-intercepts, right? Now, in the last case here, we're going to look into this quadratic function. As you can see, the graph of it is not intersecting the x-axis at all, which means that it doesn't have zeros or solutions, as we call them, or roots. So we're going to say that in this case, there are no roots. At least that's what we have said in grade 10, right? When you were first introduced to the intercepts of a quadratic function. Now, we're thinking, where do these equations come from, and how can we interpret this algebraically? So as an example, I'm going to give you a simple quadratic equation to solve. So let's say x squared plus 4 equals 0. So that means that x squared must be equal to -4. And if you want to isolate x, you would take the square root of both sides. And remember that when we take the square root of both sides, we have to take both the positive and the negative of it. So this would be equal to the square root plus minus the square root of -4. Now, we have said that the square roots of negatives do not exist, and the calculator will confirm that if you try to find the square root of -4 on a calculator. Now, why isn't root of -4 undefined? Well, we're going to say that root of -4 is undefined in the set of real numbers, but root of -4 is actually a number, but it's a number that doesn't exist in the set of real numbers. We call these imaginary or complex numbers, which is something that you learn on a separate lesson probably, but I'm just going to give you a quick idea of what that means. Now, there are numbers that don't exist in the set of real numbers, and the smallest of them is the root of -1. The root of -1 is what we call an imaginary number, and it is called the number I, or it's short for imaginary. Now, why do we consider such numbers? Well, if you have the root of -1 equal to I, and you square both sides of it, then you're going to see that the left side of the equation will become a -1, and the right side of the equation is going to be simply I. So to the power of 2. So I square equals -1. So as you can see, an imaginary and a real number can have some connection, and these are concepts that are better explained in separate lessons. I just want you to get a flavor of it at this point, but I assure you these are very, very useful in solving many problems, especially in electronics. Now, any number that is expressed, let's say, as the square root of -4, for example, is called imaginary. And very often we have imaginary numbers mixed with complex numbers. So, for example, if you have 2 plus the root of -3, that is a real number, that is an imaginary number. So this is an imaginary and this is a real number. So when we have a mixture of imaginary and real numbers, we call them complex numbers. Okay? Or in a simpler word and more general word, we call them non-real numbers. If you want, you can explore them a little bit further on ChatGPT and check and see for more information if you're curious about it, so what they are and how they're used. But we're going to stop it here, and we're going to say that equations that have no x-intercepts have two non-real, and they're always distinct, and that's something that we will discuss in other examples, roots or solutions or x-intercepts, whatever we want to call them. Now, sometimes the word non-real is replaced with the word complex. That's when you have a mixture of real and imaginary. Or if you want to be more specific, if you end up with a root like this, you may as well use a more specific word, which is imaginary, which tells us that the solution is going to be a number that is expressed as the square root of a negative number, and that's it. Now, we're going to take a look at some examples and go over the different strategies to solving quadratic equations. Now, I know that we have actually been introduced to it in the past, but we're going to go over solving by factoring first. And for this, I will continue in the next video.